All right, let's take a look at the next problem on our list. This is LeetCode number 199, binary tree right side view. Given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the orders you can see ordered from top to bottom. So I've actually seen this one in a LeetCode discussion in terms of on the CS Majors Discord. This was a really interesting problem to sort of talk about. So basically the idea is that we want the rightmost we kind of want the rightmost elements from each order. So there are multiple ways that you can tackle this. You could tackle this by doing a level order traversal, favoring the left or the right side. So you would add the right side element first, and then you would just take the right element. Or you could do a post-order traversal, which naturally favors the right side, and only print out or add the most deep element on the right of the layer. So the idea is that if we do a post-order traversal, we will add the elements, right? We'll add the elements starting on the right side. So for example, if this, and maybe if we do this visualization, toss a null there. If we do a post-order traversal on this side, then we will start with the 4, then the 3, then the 1. But what we do instead, or what we could do, let me think about this a little bit. The idea is that we also keep a track of the depth. And if it's the first element that we've seen of that depth, then because we're running in post-order traversal order, we know that that element belongs within our list. So in that case, we can just add it. In any case, both of these approaches will take O of n time, where n is the number of nodes within our tree. Because, well, in the layer order, or the level order traversal, we have to traverse over all the layers, and that's O of n, obviously. And then in post-order traversal, we traverse over the entire tree, even if we don't add elements into our list. I don't think there's really an easy way to sort of cut things off, and that is because we could potentially have an element on the left be the rightmost of the layer, right? So we actually had a tree like 1, 2. Then technically we would want to print 1 and then 2, because 2, although it is not on the right subtree, it is still the rightmost of the layer, right? So let's get started coding on this. I'm going to take a crack at the post-order traversal just so I can practice sort of the recursive approach to a problem. In the recursive approach, we're going to need the node itself, a depth, and then we'll take a reference to the list, mutable list of int. And the reason why we take the list is that, and this was a solution that was posted in, I think it was written in C++ by a super awesome member of the CS Majors community. Something that I found really smart as part of it is that instead of holding a reference, like a global static reference to a maximum depth that we've reached so far, we could just use the length of the list for all intents and purposes to know, like, so far, like the deepest that we've gone, right? Because technically the list should hold only one node from each layer. Therefore, the list length, or the size of the list, should be the maximum depth that we've reached so far. And then we can just return right side view of root depth, and then we can create a mutable list of int. And we can say if root is null, then we can just return a empty list of int, right? Empty list. And then here in this case, we can say if root is null, we'll also return. Otherwise, if depth is greater than our list.size, I think it's greater than or equal to, then we'll say list add our root. Then if root.right is not null, we'll favor the right side. So right side view root depth +1 because we're going deep. And if root.left is not null, then we'll also do a right side view afterwards. So we always favor the right side first. If we have a right side, then we'll traverse down that way first, recursively. So at 1, well, 1 is greater than the list size because initially the size is 0. So we'll add it here. Then we'll go to the right because the right side is not null. We'll go through 3. 3 is not null. So we'll go through and add that to our list. And its depth is 2 now, which is greater than 1, which is our list size. And then our root size, and then we'll traverse on the right side again and get that. And then we'll bounce back up. We'll go to the left. The left, well, this 2 is at depth equal 1, right? Or depth equals 2 rather. Sorry. Depth starts at, we'll start it at 1. Or we can start the mutable list with our root itself. And we'll start it at 0, right? Because the depth of the tree, I think, is defined as the length, the number of edges between it and the root. And in that case, the root is at depth 0. So we start at the root. Well, we added the root into this list already, so it doesn't really matter. This is depth 1. Well, that's greater than or equal to our list size. So we'll add it. And then this is, or do we want to? No, because if we do greater than or equals to, so once we add 1, 2, 3, right? This will be 3, or 1, 2. Let's see. 2. This will be 1 and 2. But at that time, the list size will be 3. So I think greater than or equal to is safe here, as long as we start our depth at 0. And then we'll define our depth is defined in this case as num edges between the root, between the node and the root. And so the depth starts at 0, but we add the root, and then we sort of explore there. And if an element happens to be like in this case, we go to the, we can do something like, let's see, how do we want to do this? The rightmost of this, we could do a null 3. I think I need another null. There you go. So in that case, we'll go left. Right side has nothing. We've already added 1. The depth here is 1. And since there's 1 element, then we add it, and then we go to the right. So this is depth 2, and we add the 3. So this should work. And in the case that there's only an element on the right side, if root is null, return. Therefore, this root should not be null here. I'm guessing it's... Let's see. We'll do a val right side, or yeah, right side is equal to mutable list of int, starting with the root. We'll pass this list in, and then we'll return our right side. Okay, so that way we can keep this as a unit return rather than anything else. I think this might save a little bit of space because we don't duplicate the list at each step. We're just passing in the reference. I'm surprised that it's not upset at me using root here and here, but I guess the compiler is smart enough to know that root or the root here is not null, but it's not smart enough to know that the root here is not null because for some reason it's not yelling at me there. Or maybe it's just not yelling at me there because it didn't catch it. It only caught this one. Let's see. Oh, wait, no, this is dot val. Whoops, I forgot that this is a mutable list of int, rather. Val. And right side. Cool. And so this should be correct. List. And we got a Stack Overflow error. Interesting. Oh. Lol. Should actually recurse on the right and left elements instead of just recursing on itself and causing a Stack Overflow error. That'd be very nice. Okay, cool. So it seems like it worked for at least those cases. Let's just toss in all of our example cases that were provided. Let's see if we run into any errors. Looks like we're fine there so far. And then let's see if there are anything else that we need to worry about. I think we're fine for now. And let's throw in a submit and let's see how far we can get. Okay, cool. It seems like we're a little bit slow. In that case, well, I mean, we're not slow by that much, but is there anywhere obvious that we could probably go faster? Well, I'm not sure if we would be fast if we instantiated the list here. It might be a little bit cleaner if we just returned that list, right? Just return here, and then we just return here also. And then we would just return the mutable list of int rather than returning a unit. But I don't see any reason to do so if we're already passing this in by reference. We could return a list instead, and in that case that would be immutable. But I'm not sure if that would actually speed things up. Yeah, this is an interesting problem. But honestly, I think I'm fine with this. Like the asymptotic runtime of it is not affected. We are very much fine with the asymptotic runtime with O of n, where n is the number of nodes, because even in the level order traversal we have the same thing. We have to traverse over all the nodes in order to grab the rightmost value. So I think I'm just going to leave this here, but in any case, I hope you learned something, and I will see you for the next problem.